Okay, good morning. So let us now continue our lesson. So last time we talked about the Pascal's identity, if you remember. So the Pascal's identity was if you have n choose r, this is equal to n choose r minus 1 plus, so let me see what was, no, that was n minus 1 r, and then you have, so you choose either r people from r minus n minus 1, or you choose r minus 1, yes? So this we had before, but I didn't prove it algebraically for you. I proved this using the combinatorial argument, if you remember. Okay, so let us try to warm up again and then prove this using algebra. And then if I want to, this is called the Pascal's identity. Pascal is a mathematician. Pascal's identity. So if I want to prove this algebraically, so I start from the right side, because this is more involved, and try to simplify that. So I will start from the right hand side. Instead of this one, so you know that the formula, let me repeat it here, I have n choose r. This number on top goes into the numerator, and then you have r factorial, and then you have the difference between them factorial, both of them in the denominator. So if I want to use this formula that you see here, this here n minus 1 plays the role of this capital N, and this little l plays the role of the capital R. So then we can write it as this fraction. This becomes n minus 1 factorial divided by r factorial n minus 1 minus r factorial. Yes, so I'm just using the formula to expand this one here. And I will do the same thing here, but here n minus 1 plays the role of the capital N, and r minus 1 plays the role of the capital R. So what can I do? I can write it as n minus 1 factorial again, and then here I have r minus 1 factorial. And then if you do it in your head, n minus 1 minus r minus 1, 1's are cancelled, and n minus r is left, yes? So if I write n minus 1 minus r minus 1, this becomes n minus 1 minus r plus 1, but then this minus 1 and that one are gone, so n minus r is left. And my goal is to simplify this as much as I can and show that the addition of these two fractions becomes this fraction here on the right. So this is clear that I have to take the common denominator. But if I want to take the common denominator, one naive approach is to multiply the denominators. Of course, this definitely will work, but it becomes hard. So in order to do that, I need to think about to optimize my choice for the common denominator. So I need to write exactly the expression which is divisible by both of them, but does not contain extra factors which I don't need. Yes? So what should I do? Instead of r factorial and r minus 1 factorial, I hope that you agree with me that I can simply choose r factorial. Because r factorial is not only divisible by r factorial itself, it is also divisible by the previous factorial. So this can serve as the common factor between these two. And if I want to write in a factor which can take the common factor between these two, what should I write? I just compare these two numbers. This is n minus r. This is n minus r, 1 unit less. So whatever this number is, this is the previous integer. So which one plays the role of the common factor for these two? Again, n minus r factorial, yes? Because n minus r factorial is not only divisible by itself, but also by any previous factorials. So you see, the optimized common denominator, which we call the least common multiple of these two, is just simply this. And then you, in your head, you divide this expression by the denominator of the first one. Okay, so let me just do it here. So if I divide this in my head, r factorial n minus r factorial by the denominator of the first fraction, and if you don't mind, instead of writing n minus 1 minus r, let me write n minus r minus 1 factorial. So what is the result? It is clear. This r factorial and that r factorial are gone. And then this one is also divisible by that. What you need to write it in your head as n minus r times the previous number factorial, yes? And then this one also cancels that. So if I ask you, if I divide this denominator to the denominator of the first fraction, what the answer is simply n minus r. And then I have to multiply that factor into the numerator of this expression. So this becomes n minus r multiplied by n minus 1 factorial. Yes? And then I will do the same thing. So I have addition here. I can go to a scratch word, r factorial, n minus r factorial is my common denominator. I divide this in my head by that one. This is even simpler. Yes, so what's the answer? This one and that one are gone. In your head, you can write r factorial as r times r minus 1 factorial, and this one and that one are gone. So what is left for me is just simply r, and I have to multiply that r into the numerator, yes? Okay, how should I continue now? It's very clear. Yes?
And minus 1 factorial is cancelled out?
Not cancel out. I have to pull it out.
Yeah,
factor it out. So there's nothing to cancel this out with that. But I can n minus 1 factorial appears here and there as well, so I can take it out. So what is left from the first one is just simply n minus r, and then what is left from the second one is just simply positive r. And then on the denominator, I will have the same r factorial n minus r factorial repeated. But immediately you see that what is happening now is this r and that r are canceled. So n is left, which will be multiplied by the previous number factorial divided by, I don't just copy and paste the denominator. So what can I write in the numerator? N times the previous factorial is n factorial, yes? So I just combine it into the form of n factorial divided by r factorial n minus r factorial. But this is also very famous formula. The formula is just n choose r, and this is equal to the left-hand side, yes? So this is the algebraic way of proving Pascal's identity. And we also proved this in a different way last time, if you remember, using combinatorial arguments.
Fallback?
Yes?
It's n minus r, not n minus 1.
Yes, thank you. Thank you. Okay, so now, for example, this is also good to understand it in both directions. Usually, if you want to use this to simplify things, it's better to go from the right-hand side to the left-hand side. How can I interpret that? I would say to myself that if I have two of these numbers, but they have the same number on top, and then the numbers below differ by 1. Then if I want to, I can combine them into one of these symbols. But how should I do that? I need to add 1 unit to the top one and write it on the top. And between these two, I need to choose the bigger one and write it here. So I don't know how you can interpret it in your own language. So you need to detect a pattern. So if I have two of these, in which these numbers are exactly the same and these numbers differ only by 1 unit, if you want to, you can combine them into one single of these symbols. But how I need to add 1 unit to the common number on top, and then I have to choose the maximum one between them. For example, if I ask you, what is 5, I don't know, 3, and then, so let me make it 2, and then plus 5, 3. For example, can I simplify? Of course, one way, if I ask you to calculate that, you can calculate the first one, calculate the second one individually, and add them. Yes, that's a different story. But if you want to see that, can you write this sum as one single symbol like that? The answer is yes, because it is following the Pascal's pattern. How I should see that? I see that the numbers on top are equal, and I see the numbers below differ exactly by 1. So according to the Pascal's identity, I can combine them into one of these symbols by adding 1 unit to the top one, which is 6, and between these two, I choose the bigger one, which is 3. So I haven't calculated what the number is, but I was able to convince myself whatever this sum is, this is equal to this single unit. Okay? So let me just try to give you some examples. For example, how can we simplify this? So I have 10 choose 3 plus 2, 10 choose 4, and then I have, I think, 10 choose 5. Can I simplify this into one of these symbols, but a unique symbol, okay? Here I have 1, 2, 3 terms. Without doing algebraic calculations, I want to combine all of these symbols into one of these choosing symbols, yes? So is it possible to do that? Of course, this I have engineered that in a way that you should use the Pascal's identity in some way to be able to answer this question. So I just want you to understand, calculating this is a different story. I don't want you to calculate that because, for example, you can put these numbers in the calculator and get the answer. That is not the goal. I want you to be able to write this in the form of one single of these symbols. Okay? And of course, this is an example in Pascal's identity. So definitely this identity is relevant. But then you have to be a little bit creative to see how can you use this identity to simplify that. Any ideas? Yes?
You can look at it like 10 choose 3, 10 choose 4, 10 choose 4, 10 choose 5.
Exactly. So you are breaking the middle one into two of them. Yeah, exactly. So I will do that. So this becomes 10, 3, yes, and then plus 10, 4, and then again plus 10, 4, and then plus 10, 5, yes?
Yes.
10 choose 5. So, and then is it a Pascal identity appearing here?
Yes.
Yes, because this is the following, that is exactly following the pattern I described. These numbers on top are exactly the same. These numbers differ exactly by 1, and that's the same pattern here. So can I combine these two into one?
11, 4.
If I want to do that, I have to write, instead of this, what I can write here is 1 unit more, so that's 11, and between these numbers I choose the bigger one, and then for these two I can do the same thing, so it is 11,
5.
and then that's 5, and then I have to add them. But coincidentally, this also becomes another Pascal pattern, so what can I do?
You add 1 to the
Which is
top number, 12.
12 and
5.
5. So that's good. So whatever this number is, that's equal to 12, 5. Can I also write it as 12 over 7? That's just a repetition.
Probably.
Yes. Did we talk about these things, yes, or not? We talked about the combinatorial proof of that Pascal identity.
Maybe we talked about it when they were here.
No, I think we talked about it. I just don't remember.
Okay. Okay, anyway. So this is, for example, why combinatorial argument, why this is correct. We had another formula that if I have nm and if I have nr, if these two numbers add to n, then these two symbols are the same. And the reason behind that is that assume that I have 12 students. I want to choose 5 of them to take them with me. Of course, this is the natural way to do, but instead of if I am a little bit impaired from my brain point of view, I will choose the people I'm not taking with me. So if I choose 5 people with me among 12 students, it means that I am choosing 7 people not to take with me. So the number of ways that I can do these things probably are the same. Okay, but another problem, let me just write a little bit more interesting one. This is not exactly Pascal identity. You need to do some engineering to make it a Pascal identity. So 2, 2, 2 choose 2, 3 choose 2, 4 choose 2, and then we continue up to 100 choose 2. Okay, so immediately you realize that this is not exactly the Pascal identity, because for Pascal identity to be able to combine them into a simpler one, I have to have these two different, yes, at least by 1 unit. Okay, can you see how can I engineer the problem that Pascal identity becomes useful? Yes, please.
You could rewrite 3, 2 as 2, 1. And
3, 2 as 2, 1? No, this is not possible. Yes, 3, 2, 3 choose, this is red, 3 choose 2. It is not equal to 2 choose 1.
yes, but
It is equal to choose 3, 1. 3 choose 1. This is correct because 1 plus 2 becomes 3, and of course these two symbols are the same. That is what I mentioned here. You see, these numbers are the same. If you want to use that rule, yes.
Maybe if you take that n choose r minus n minus 1 choose r, it's the same as n minus 1 r minus 1.
May you repeat?
So
Okay, so
And
are
choose
you using the Pascal identity?
Yeah.
So, okay, so what you are saying, on which pair you want to use the Pascal identity?
first on the first pair, I guess.
So is it possible to do it on the first pair? Because if I want to do it on the first pair, I have to have them equal.
Yeah, but if you take the identity and then you take as n choose r and then move n minus 1 choose r to the other side.
And then
So you substitute
this becomes negative then.
Yeah.
But I don't have negative sign here.
But then you have a negative sign in the other one instead. So
Okay, so let me follow what you are saying. So you are saying that move the other one to the other side.
Yeah.
So I have n choose r minus which one you want to move to the other side, the first one or the second one?
choose r.
N minus 1 choose r, yes. And then what is left for me on the other side is n minus 1 r minus 1, yes? Okay, then what? Because if you want, this is my impression, if you want to use this, you need to have a subtraction in between. You don't have it. But that was good actually. It didn't work, but might be give you some idea. So here, so that's, you need to think about this in this way. I need to have them the same. Is there any way that I can write this in a form that the top number is 3 rather than 2?
3 choose 3.
Yes, why?
Because it equals to 1. Or
Yeah, because this means the number of ways that I can choose 2 people from a group of 2 people. And then 3 choose 3 is the number of ways that I can choose 3 people out of 3 people. In both cases, I have the answer to be 1. So that's the idea. That's the idea. So instead of writing it, so I mean, this is the way to think about the problem. Okay, don't deviate yourself. Don't try to think in a converging way. Yes. So you say that I need these numbers to be equal. This is the first impression comes to you. Okay. Of course, this might be a hard problem if I give it in the exam out of the blue. But now we are talking about Pascal's identity. So if I'm not crazy, I will give you examples related to Pascal identity. I will not give you examples related to the derivative, yes? So then, this is by the way, this is a way that you need to think about, and that is also another branch of mathematics called game theory, yes? So you need to see that if people are rational, So yeah, so that's also part of mathematics. So if you think rationally, you will understand that this example is an example and not Pascal's identity. The natural question to ask is that what I need if I want to use Pascal identity. Okay, if you narrow it down, you will see that you need these numbers to be equal. They are not equal. So the natural question to my brain is to ask, is there any way to make them the same? Of course, if I get disappointed, I will try to work out some other way if I want to succeed to solve the problem. But isn't it the most natural one to make them the same? If you insist to use the Pascal's identity, which is a natural move to do here. Okay, so if it comes to your mind, then you replace this one with what? 3, 3. Yes? And then you copy and paste the rest of it. Okay. And then you see that at least I have a pair following the Pascal's identity, yes? So what is the answer to this part?
4, 3.
4, 3. But then I hope that you understand what is going on.
5,
What is going on? This one with the next one makes another pair of Pascal identity, which is
5,
5, 3. And then what is coming next, for example, in this dot dot? This is coming 5, 2.
Yes.
So this one with the next one makes another Pascal identity. So this becomes 6, what?
6, 3.
6, 3. And hopefully you can continue this pattern. What do you think will be the last answer?
101, 3.
Yeah, 101, 3. 101, choose 3. Okay, that's also one way of thinking about the problem. Okay, there are some interesting problems in the book. They have appeared in the exercises. I don't know why they have done that, but let us try to solve those problems here. So the problem is that I don't know how to motivate you. For example, assume that you go to a flower shop. Is there any particular name for a flower shop in English? I think there is, yes. Anyway, so if you go to a flower shop and you want to buy, I don't know, a bouquet for, I don't know, for your girlfriend or something, and then you have 5 types of flowers there. So let me call them flower 1, flower 2. I don't mean one flower. You have flower 1 type of flowers. Usually you have enough number of them if you want to choose. Flower 2, flower 3, and flower 4. Okay? And then you want to choose, you want to make a bouquet of, say, 3 branches of flower. Okay? Of course, you also need to check your pocket, how much money you have in your pocket, but let us assume that you have enough money for 3 branches of flower, okay, to make your bouquet. In how many ways you can do that? That's a good question. I just want you to understand the question. So you go to a flower shop. There are enough branches of each one of these types of flowers. You want to make a bouquet out for 3, consisting of 3 branches of flower. But that's up to you to decide. For example, one way is to choose all of them of type 1. You can choose all of them of type 3. You can choose one of them of this type, one of them of that type, one of them of that type, and so forth, yes? So in how many ways you can do that? And that's not an easy question. Just, yeah, tell me.
I thought it was 4, choose 3.
No, but 4, choose 3 doesn't allow for repetition. Yes? When you say, first, 4, choose 3, what does it mean?
Is it that you pick 3 different?
Yeah, so 3 different. So you're not allowed to repeat. So this counts the number of combinations of F1, F2, F3, and F4, or 3 combinations. For example, one combination is F1, F2, F3. And of course, you agree with me that order doesn't matter. If you take your bouquet, it doesn't matter in which order you make them. So it's a combinatorial problem for sure. But this doesn't allow for this situation. Yes? So the number that you're supposed to count, if you write this, it means that you want to have branches of your flowers all distinct. In that case, you are right. That's the answer. But now I lift that actually limitation. So how many ways we can do that? Solving this problem is actually interesting because you have to be very creative to be able to solve that problem. Any ideas?
Can you do 4 choose 1 or 3 times?
No. Why is that? Of course, if you want to do that, you can start counting these possibilities and add it on top of that. But if there is a way that you can come up with the answer in one go, it is preferable to do it in that way. That's my goal here. Okay, forget about this problem. Let me now start a new problem, and I write an equation. It's completely abstract. This is in the real life, but this is more or less what I'm saying is abstract mathematics. So I have an equation, x1, x2 plus x3 plus x4 equals to 3. Okay, forget about the first problem. Now let me mention a new problem. This problem, I want to count the number of non-negative integer solutions to this equation. Okay? So that if we can solve that problem. So for example, one integer solution of this is I take this one to be 1, I take this one to be 0, I take this one to be 2, I take this one to be 0. This is one solution, 1, 0, 2, 0. If you add them up, it becomes 3. None of them is negative, all of them are integers. Okay, but this is not the only solution, of course. What is the other solution? For example, what can I say? I can take this one here, I can say that I can keep the same numbers, but I can write it like this. Yes. This is a different solution for this equation because now x1 is 1 as before, but x2 is 2 rather than being 0. So this is a different solution to that. Now my question is that if I start listing all possible solutions of this equation with one constraint, I am only able to choose non-negative integers for solutions. Then how many solutions you can list? Can you give me another solution, for example? Another solution is 1, 1, 0, 1. Yes, this is also one solution. Another solution in the extreme case, okay? 0, 3, 0, 0. That's also one solution. And then we want to solve that problem. After we solve that problem, we want to find the connection between this abstract mathematical problem with this more realistic, real-life problem, okay? So how can we solve that problem? How many solutions I can write down in my list? The method that you need to answer the second part is very interesting. So it shows that how smart you need to be sometimes in order to be do some calculus counting problems. Okay, so the way that the book is describing in the text of the problem itself, I want to just more or less repeat that for yourself. Okay, so here, what I want to do, I want to take 3 zeros. Okay, that's a little bit bad example, but let me just write it. But that's anyway. 3 zeros and 3 ones. Okay, but I don't look at zeros as zeros. I look at zeros as separators. Okay, what do I mean? Let us arrange these zeros and ones in a row in any way that you like. Then I want to interpret that arrangement as a solution to this equation. Okay, so for example, one way of arrangement, do you agree, is that I choose 0, for example, and then I put 2 ones, for example, and then 2 of them are gone, 1 of them are gone, I put a 0, I put a 1, then what is left for me? another 0. Okay, and now I am telling you, look at these zeros as separators. Okay, so what does it mean? It means that whatever you see before the first 0, the number of ones appearing before the 0, I consider it x1. Okay? The number of ones appearing between the next two zeros, I consider it to be x2. And the number of ones between the next zeros, I consider it to be x3. And the number of ones appearing from the last 0, I consider it x4. So for example, you see, by this code, so assume that, I don't know, I am a Russian guy, I don't know, I want to communicate with you. I write you this code, but you understand how to decipher the code to find the answer to that question. How do you decipher that? You say that, okay, I don't consider zeros as zeros usually. I consider zeros as my separators. So before zeros, how many ones appear?
0.
0. So I interpret this by x1 is 0. And then between these two zeros, how many x's you see? How many ones you see?
2.
2. I will read it in this way, that x2 is 2. Okay? And then between these two zeros, what is the meaning? 1 appears, so there is only 1, and then after that is 0. So if I transfer this code to my colleague in another country doing some spy work, then this will decipher it like this. Is that understandable? Okay? And now let me ask you the other way around. Now you're in Russia, okay? You want to decipher this answer. How do you code that answer? This answer. If you learn that what I'm doing here. I want you to code this. Yes?
1, 0, 1.
So just let me 1, 0,
1,
1,
0, 0, 1.
0, 0, 1. Okay? So let us check. I told you that the zeros are separators. So before the first 0, the number of ones that appear is 1. So I will consider it x1 to be 1. And then between this 0 and that 0, 1 again appears. So I consider it to be x2 to be 1. Between these zeros, no ones are there. So it means that x3 should be interpreted as 0. And then after this 0 is what? Is 1. So you are right. So you were able to code this answer as a binary code. Is that clear? So what I am doing, these are not binary codes, yes? So this is a binary code accidentally, but not all of them are binary codes. So I am using 3, 2, and there, okay? But I am coding all my solutions to this equation in a very creative way, which was explained in the book, as a binary code, yes? So if you see the binary code, you can translate it to the solution of that equation, and vice versa. Any solution to this equation can be encoded into a binary code. Yes? And this is a unique way of doing things. There is no misunderstanding here. So if you receive this code and you know the rule, you will definitely decipher it only in this way, not other way. So this means that instead of counting the number of solutions here, I can simply count the binary codes, because they are in one-to-one correspondence. Is that understandable? When I give you the answers, when I give you one solution, you can give me exactly one binary code. And if I give you one binary code, you will give me exactly one solution there. So hopefully you are convinced that the number of binary codes constructed in this creative way is in one-to-one correspondence with the number of non-integer solutions, non-negative integer solutions to that equation. So you can put this problem aside. This problem is different from this problem, but in the world of counting the possibilities, the numbers are the same. So it doesn't matter if I count these number of solutions or these number of binary codes. This is understandable or not? Okay, now leave that problem and look at this one. How many zeros you see? 3. How many ones you see? 3. and then I'm using all of them in a row. How many ways I can arrange these into this binary code? So my question is that I give you 3 zeros, 3 ones. Count all possible binary codes. This you should be able to do if you have done your homework, okay? Yes?
Is it 6 factorial?
No, 6 factorial is in the case, don't mix things up, don't disappoint me, okay? 6 factorial appears if all 6 items are distinct. But here 3 of them are of type 0, 3 of them are of type 1. So the answer of 6 factorial is too naive, yes? So what's the answer?
6 factorial divided by 3 factorial multiplied by 3 factorial.
Exactly. So divided by, so one answer is this one. So this is 6 factorial, which you said. It is not working here because we already learned permutations with repetitions, if I'm going to use all. So 0 is repeated 3 times. If you have forgotten, you can go back and watch the videos again. So this I divide by 3 factorial because of 3 zeros, and then I have 3 ones, I have to divide by 3 factorial itself. And by the way, so this is the correct answer. And that's the correct answer. So how many ways are there? So this is 720 divided by 6, 120 divided by 620. So if you don't believe you you need to be patient to list all of them. So there are 20 solutions there. Okay? But that's not my point. Can you write this as a combination formula?
Yes, I would 6 choose 3.
6 choose 3. So that's also 6 choose 3. This is algebraic way of understanding that. Okay? But can you also understand, could you write this answer directly without going, by the way, if in the exam you write, that's completely okay. But could you write this example, this answer, without going through permutations, just by looking at combinations? Remember, permutations respect the order. Combination does not respect the order. Is my problem respecting the order or not? It is.
Yes.
So it might be a little bit weird. How can I use combination for a problem that respects order? But you need to, if you understand it, that is possible. How can I do that? I would say to myself, for writing a code, a binary code here, how many locations do I need? I need 6 locations, yes? So location 1, so let me write it like this. Location 1, 2, 3, 4, 5, 6. So I need to fill up these locations either with zeros or ones. And then I give you another color and I ask you to mark 3 of them only. Okay, so how do you mark them? For example, you mark this one and this mark and that one. Now, do you think marking respects order? No, it respects a combination of marking. If I replace these 2 marks, you cannot recognize the difference. So, now how many ways you can mark these locations? 3 of these 6 locations. How many ways you can mark them? Yes.
Is it 6 choose 3?
Yes. The answer is that. Okay, but how can I interpret the answer? I would, yes?
You just say that marks are zeros.
Yeah, mark are zeros or ones. So when I see your marks, I take my 3 zeros and place them in the places that you mark them for me. But all of them are zeros. In how many ways I can take 3 zeros and put them in these 3? How many ways?
Factorial?
Just one.
Oh, sorry.
Because I have 3 zeros. It doesn't matter if I change this 0 with that 0. So when you are done, you can do it in 6 choose 3 ways. This is the ways that you can mark these things. But after your marking is finished, you drop the pen and you leave the classroom. Now my duty starts to fill up these crosses with zeros. So I have 3 zeros in my hand. All of them are identical because they are zeros, and then I have 3 identical crosses. And I want to put these 3 zeros into these 3 crosses. How many ways I can do that? Just one way, yes? I put 0 here, 0 here, and 0 here. And then what is left for me? 3 locations are left and 3 ones are left. And I want to put these 3 ones into 3 locations. Even though the locations are distinct, I agree, but the ones are not distinct. So it doesn't matter how I put them, so I have to fill up them with ones. So you see, this interpretation is correct solving a problem in which order matters using combination. But this problem was also possible to do it by just looking at permutations. But if you use this is permutation with repetition, and if you just do that, this is just using combination. Is that clear? But one more question. Do you think there is a connection between this abstract problem with the problem of choosing flowers there? Yes?
It's just the same problem.
They are the same problem. Yes? How can you interpret that? Can you say,
You
so what is x1 here?
first flower or flower one.
Not first flower. Be precise in
The
mathematics.
flower one.
No. The number of the
Oh, yeah.
choices of flower 1. So I would say that x1, I can assume that x1 is the number of flowers of type 1 that I choose. x2 is the number of flowers of type 2 that I choose, and the same for x3, x4. Because the restriction is to choose 3 branches of flower, no matter how I choose my flowers, the sum of these choices should be exactly equal to 3. Is that right? Is it clear for everyone? So that's what we solved the problem. So the answer to this problem is 20. So because if you calculate this number, it becomes 20. Yes? So this means that in 20 ways, I can choose 3 branches of flower out of 4 types of flowers. So this is sometimes in the books, they are called combination with repetition. Because you remember, as Gustav mentioned in the beginning, so for choose 3 is considering all 3 combinations, but repetition is not allowed. But here, I am looking at a combination problem. Why it's a combination problem? Because it doesn't matter how you make your bouquet. If flower 1 is coming first or flower 2, in the bouquet, the combination of the flower types are important, yes? So this means that, yes, this is not the correct answer. This obliges me, or it forces me to choose 1 only of each type if I want to, at most. Okay, but I want to have the freedom to choose more than 1 if I want to. So that is usually in books called combination with repetition. Is that clear? Okay. So for example, let me see if you understand the problem in this way. You can make up stories, yeah? So for example, let me go to a restaurant, for example, that contains only 2 foods, yes? So food number, now let me make it more interesting. So food 1, food 2, usually in Sweden it's common, yes? In restaurants you have meat, chicken or fish, and vegetarian, yes? So you have these 3 types of foods, and then you want to invite your friends. For example, you have 7 friends. And then you want to give them the option to choose whatever they like to. Okay? So, but they have to choose only 1 food, okay? If they don't fill up with 1 food, that's their own problem, yes? Okay, but now how should you do that? How should you look at this problem? In how many ways your friends can choose foods? I just want you to understand, because I want to make it, I want to give the formula for you at the end by understanding this problem, yes? So you have 7 friends, but you have 3 types of foods, and then you want to give them the opportunity to choose 1 food, but whatever they liked. In how many ways you expect that they can do this choosing? So assume that you don't know which one is vegetarian, so you don't know, really don't know. Okay, so what happens here? So if I want to write something in English for x1, something similar to this, can you tell me what is x1 here? What is x1? Yes?
You mean F1?
Not F1. Be precise.
X1 is equal to F1.
No.
The number of
X1. Yeah.
number of F. Number of
Even better. Yes, you are right, but even better. You don't hesitate, yes, to use words. You don't need to pay taxes for the words you're using. Yes?
Food type number 1. X is
X1 is not food type number 1. I understand you understand the problem, but you're trying to be economical when using words, yes? Yes?
Is it the amount of people that chose a certain food?
No.
No.
No. Amount means the number.
Yeah, the number.
No, that is not that the correct interpretation. That's why I'm asking you, because I want you to understand the difference, because there are two numbers involved here. The types of foods, the number of friends. That's, I want you to be precise. When you say X1, what is X1? Yes, Mario?
The number of food types, maybe?
No, the number of food types means 3. So if X1 is 3, then there is nothing to solve.
Like the amount of like, I don't know how to say it. Like,
No, but you need to know how to say it. Yes?
X1 corresponds to the number of people who chose food F1.
Yes, I think it's correct. I'm also confused. So do you make it in a little bit? I think you were. Can you repeat it?
X1 corresponds to the number of people who chose the food type F1.
Yes. Why is this good choice good? Because what he is saying is that let me write xi. Xi is the number of what? The number of friends choosing food type I. Yes? Is that right? So xi is the number of friends choosing food type I. If I have this one, so how many x's you expect? 3 x's or 7 x's?
3.
Is that right?
3 X's.
3. So it means x1 is the number of friends choosing food type 1, x2 is the number of friends choosing. Okay. And then what is the constraint on x1, x2, x3?
They should be equal to 7.
No. Be careful. Yeah, I mean, you understand what you say, but the sum of them should be equal to 7. So it means that x1 plus x2 plus x3 is equal to 7. Yes? Because the reason that I was a little bit careful in understanding, because some people get confused. They write x1 up to x7 equals to 3. There are two numbers involved. I want you to understand. Is that understandable? I say to myself, because I have 7 friends, I should have 7 foods after it is delivered to me. Okay? The number of foods type 1, I don't know how many of them will choose type 1. Some of them will choose type 1. Might be none of them, of course. Some of them might choose X2, some of food 2, some of them might choose food 3. But in any way they do it, I know something. I know the sum of them should be 7. Yes?
So if you do it the same way as the previous problem,
Yes?
does the answer then become 10 through 7 or 10 through 3?
So let us check. I haven't checked that. So 10, what you said?
10 in 3 or 10 in 7.
Okay, both of them are the same. You are right. Let us check if that's correct. No. There is a small difference because I remember the formula for it. I think you made a small mistake. Let us understand that, okay? So now you understand, to solve that problem, I need to know how many non-negative integers are there for this equation. Is that clear, first of all? Okay? So you can just throw the main problem away and look at this more abstract mathematical problem. Yes? And then this idea I already told you. Now, do you remember when I wanted to solve that problem, I offered 3 zeros and offered 3 ones. But now can you tell me how many zeros and how many ones I need in this problem? Let us give the opportunity to Gustav this time, yes?
Maybe it's 7 zeros and 7 ones.
No. Be careful. What did I say about zeros? Do you remember? I used a word. I don't know if it's the best English word, but I think it is. What did I say for zeros? I look at zeros as
Empty spaces.
no, not empty separators. Yes. So how many separators you need?
2. So that
Two.
it should be 9 for.
Yeah, you need 2 separators because how many variables you have? You have 3. If I give you 2 zeros, then how many empty spaces I have? 1 empty space,
Yeah.
the second empty space, the third empty space, and I need exactly 3. Is that clear? So this is the number of zeros and the number of ones actually matter in this problem. Okay, so let us just check. So you told me that I need 2 zeros because by 2 zeros I will have 3 empty spaces. The number of ones here appearing here can be translated to the value for x1. The number of ones accumulated in this empty space can be considered as the number x2, and the number of ones accumulated in this location will be considered as x3. Yes. So, but how many ones I need?
7.
7 ones. I need 7 ones because the sum is supposed to be 7. Yes, is that understandable or not? Okay, so I have 7 ones, I have 2 zeros, and I have 7 ones. And this is 7. So the question is that how many binary codes that I can make with them? Yes.
Can you explain why we have the same amount of zeros and ones in the last question?
No, because in the last question it was a coincidence. How that was, if you remember, I told you it's not a good question because I was not careful in designing that. So x1, x2, x3, x4, I need 4 empty spaces.
Yes.
So I need 3 separators.
Mhm.
And then because the sum is also coincidentally 3,
Yeah.
I need 3 separators, which are zeros, and 3 ones.
So if it were to be equal to 7 or
Yes.
18 or something,
Yes.
then you should have that amount of ones.
Yes.
But still the same amount of zeros.
Yes.
Okay.
Yes. So the number of zeros, can you see the pattern? The number of zeros is
Minus the like.
1 unit less
Yeah, exactly.
than the number of variables.
Yes.
Yes? So that is because I want give the role of separators to them. Yes?
Okay. Yeah.
Okay. So that's it. And now can you tell me how many binary codes I can make here?
9 through 3.
Yeah, so I say that, okay, one way is just thinking about it purely from permutation point of view. So you say that how many objects I have? I have 9 objects, but 2 of them are of one type, so I divide by a 2 factorial for that, and 7 of them are of that type. So that's one way, by looking at the problem just by permutation. But you can also, as I described, you can take the orange marker and just cross the points you want, the locations you want. You can imagine that this becomes what? 9, 7, or if you like to, 9, 2. Also, all of them are correct. Okay? So the number that I am interested in is this number in any way. Yes?
So it's 9 because there's total of 9 numbers, zeros and ones.
Yes.
And why did you pick 2 then? It is 2 number.
No, because I picked this algebraically. So because, by the way, when you ask these questions from me, I can answer them in 2 different levels. One, algebraic level, which is very trivial. This formula is the answer to this one, but also the answer to this one as well. Because if I ask you to expand that, what do? You write 9 factorial on top, you put 2 factorial, and the difference between them, which is 7 factorial.
Yeah.
If I ask you to open this up, you put 9 factorial up there, and then you put 7 factorial here, and the difference between them, which is 2 factorial, but they are the same numbers. So one way of answering these sorts of questions is algebra. Another one, which I prefer to do it in the combinatorics, is combinatorial arguments. Yes. So why? So here I didn't do a combinatorial argument going from here. If you want to have the combinatorial argument for that, I will pick how many locations? 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, and I give you a different color marker, and I ask you mark 2 places for me. Okay, so for example, you mark 2 places for me.
Yeah.
In how many ways you can mark 2 places for me? I would say that I have 9 distinct locations, and I want to choose 2 of them.
Yeah.
And then I come back and take over. I say that, okay, when I see your crosses, I put my zeros there, and I put my ones in the rest. But I can put my zeros in your locations only in one way. Because 0, if I put 0 here, it doesn't matter if I change these two zeros, that would be the same situation. And then in these locations, even though the locations are distinct, but the objects that I have are the same, so in how many ways I can put these ones there? Just only one way. So I can multiply it by 1, multiply it by 1, if you want to, but I don't write them down. Yes. So anyway, I hope that you understand, but this is a very interesting problem. So you see, you want to solve that problem, you need to interpret it in the language, for example, of equations, and then instead of writing the solutions, you can imagine it as a binary code, which in principle has nothing to do with these equations directly. Yes? So you have to have an interpretation of how you can decipher the binary code to a solution to this equation if you are on the other side of spying. And if you want to send the code, you need to know how to code it. Yes? So this one-to-one correspondence is actually very powerful in combinatorics. Okay. So I hope that you enjoyed the problem. The problem is very interesting and exciting, okay? So for example, let me make it a little bit harder. Not harder, to test your understanding. So assume that for some reason, okay, so you, of course this doesn't make sense. So assume that you are not interested in, so let me go to abstract level, okay, here. So assume that I want the minimum value of my choices to be 1, not 0. Here, the minimum value was 0, yes? But let us say that I want to have 1 as my minimum value. So how can I solve that problem? In other words, how many solutions are there to this equation if the numbers are natural numbers? 0 is not acceptable. So all of them are not acceptable anymore because they are using 0 somewhere. Let us come back to this problem and let me give you an extra condition. Okay, so let us work in abstract mathematics here. So I have this equation, x1, x2, x3 equals to 7. I give you some constraint. I say that, for example, let us assume that x1 should be at least 1. And then I ask you how many solutions are there. So it means that I am not allowed to choose 0 for x1. Okay, then how can I solve the problem? In this problem that we solved, we were allowed to use 0 for any of these variables if we want to. Yes?
Can you just remove one place from, so you just remove one of the ones? So it becomes 8 places in total, because that one will always be there, so you don't need to choose it.
So you mean that you start with a 1?
Yeah, or you don't even need to have it in the first place.
I cannot answer quickly. I need to understand what you say. So you say that you want to go back and do the same thing from scratch.
Yeah, but so let's say we just write down the number of spaces.
Uh-huh.
And then we can just write one of the ones permanently at one end, because it will always be there. So you can just remove one of the ones. So you don't. So instead, it becomes 8 spaces.
Exactly.
Yeah.
That's one way of thinking about it. Yeah, that's correct. So what he's saying is that because when you say that because you know that still how many separators you need?
You still need the same amount of separators.
The same number of, so which is in this case 2 separators. So I need 2 zeros. In total, so was that our problem? No, it was 7. Was it right? Yes. Okay, but now how many ones I have? Still I have 7 ones. But when I want to distribute them, I take one of those ones and put it here. Because for x1, this is not the case that it can be empty here. Because I am saying that I want to have at least 1 for 1. So it means that from these 7 ones that I have in my hand, I take one of them and put it here because I don't want to give the opportunity to the first one to be 0. It has to, okay? And then one of them is gone from my list. And I don't even need to do that. That one is there. Yes? But how many of these ones are left? 6 of them. But still I start distributing them. Am I allowed to put this again here? Yes. But in any way, even if I don't put it there, but still I have one there. So this is, I'm respecting this condition. But if I put more ones there, I am going beyond that one. Is that understandable? Okay, so you are right. So you can put it here. Can you tell me what the answer is? So I myself prefer to work with binary codes in the permutation way. So how many objects I have?
8.
I have 8 objects, so 8 factorial to the numerator, but how many zeros I have? 2 factorial, and then I have 6 factorial. That's correct. Is that right? This is one way of looking at the problem. But another way of looking at the problem is just mainly introducing a new capital X1. And I say that I introduce capital X1 to be little x1 minus 1. This is algebraic way of doing that. If x1 is at least 1, what is at least capital X1? What is the low, if I want to have the lowest value for x1 to be 1, what is the lowest possible value for capital X1?
0.
0. So then, if I do the substitution, x1 becomes capital X1 plus 1, and I replace it back into my equation. Instead of x1, I have to write capital X1 plus 1, and then I have little x2 plus little x3 equals to 7. And then you see that what is happening, this 1 moves to the other side, gives me the same effect. Yes, so this becomes capital X1, little x2, little x3 is equal to 6, not 7. So I can solve this problem as I learned before. But the names of my variables are not little x1, little x2, little x3. One of them is capital, but it doesn't matter. Okay? Is that clear? Okay, now I want to test your understanding. Can you give me the formula which is in this problem? So let us assume that I have n variables and r at the end. Can you tell me what will be the general formula for the number of non-negative integer solutions to this equation? Instead of having 3 or 4 variables, let me assume that I have n variables. And instead of having 3 or 7, let me assume that I have r. Okay? And if I ask you how many non-negative integer solutions you expect because of this pattern that we learned, I want to wait for you. So then the number of non-negative, so the number of solutions in the set of non-negative integers is equal to, this is the question in the book, is equal to what? Can you write this for me as a, yes?
R minus n minus 1 and then R of the one.
No. I remember the formula, it's not that.
But maybe it can be interchanged to be the same.
No, tell me something, okay? Don't make trouble for me. Just say something, I write it down. Yes. What did you say? On top?
R plus n minus 1.
Yes, that you said R minus n minus
I
1.
mixed it up.
Okay, so that's correct. And then?
And then R. Or n minus 1.
Or n minus. Thank you very much. That's correct. That's correct. Yes. If I remember. Yeah, that's correct. But let us try to understand that. Okay, let me see how much you understand. How many zeros I need? How many ones I need? Zeros are playing the role of separators. So how many separators do I need?
N minus 1.
N minus 1. Yes, because there are n variables. I need n minus 1 zeros. And how many ones I need? Because I want to have the sum to be R, so I need R ones. Do you agree or not? Okay? So then the problem is what? How many objects you see. For me, I don't know. For me, it's easier to look at permutations. Okay? So I have how many objects? I have R plus n minus 1 total objects. I would write a factorial, but unfortunately some of them are repeating themselves, so I need to divide by n minus 1 factorial and R factorial. Okay, this is just purely permutation way, and that method that I described for crossing and things like that gives rise to that one. Of course, algebraically, this number is equal to that number is equal to that number. So this is the formula that you see in the book. I don't know which one is that, but both of them are correct. Is that clear? Yes or no? Okay, so now let me ask you another question. So how many solutions are there? Again, when I talk about the solutions, I mean non-negative integers, okay? For this inequality, let me make it less than or equal to 7. Can you solve that?
Just one question. When you wrote R plus M minus 1, choose R minus 1.
Yes?
Is that incorrect?
I think it's an N, but it's written
Yes,
poorly.
should it not be
No, this is n minus 1. Yes, thank you very much. Thank you for correcting. That was Tino's fault, actually.
No, I said N minus 1.
So why didn't you correct me then?
I thought it was just
You
a
need to
poorly
feel,
written N.
no. Either you have to trust yourself or you have to feel responsibility, yes? No, but thank you very much for correcting. Okay, now if I ask you to solve, if I ask you how many solutions are there to this inequality, then what do you say? The way that we can solve this is crazy beautiful. Okay? So I don't know, of course, it depends what you consider as beauty, but there is a natural way that you should be able to do it. And it is really relevant to what we discussed today. It's very natural. Don't say I cannot. I mean, the long way, which is not beautiful, it's brute force way of doing things, which sometimes we have to, is not hard at all. It should come to your head with a matter of seconds. Yeah, the strategy should come to your head in a matter of seconds. Okay, so it means that the seconds in my head and seconds in your head are different, yes? So it's a little bit of relativity here involved. Now if I ask you to write solutions, instead of x1 plus x2 plus x3 to be 7, you have more degrees of freedom or less degrees of freedom? More. Because in the equality case, you have to make it exactly 7, but here, you don't need to make it exactly 7. Exactly 7 is one of the choices, but, come on, but,
Can be anything larger than 7.
no, I want to see how many ways I can make the sum of these three numbers in the set of non-negative integers less than or equal to 7. Don't you think that if I count the number of ways it becomes 7, and then the number of ways it becomes 6, and then the number of ways it becomes 5, and then add them up, it becomes the answer I am demanding? Yes or no? Because it cannot be 6.5. Because there is one constraint. I told you, you have to choose them integers. Okay? So it means that this problem, the number of ways that I can respect this condition is equal to the number of ways that I can respect this condition, or yes, if I respect all these conditions, this happens if and only if one of them happens, and they cannot happen simultaneously. Is it understandable or not? They cannot happen simultaneously, because if this is 0 simultaneously, it cannot be 1. Yes, so it means that if I ask you, can you count the number of ways I can fit this and this and this separately and add them up, you see that this becomes the number I am interested in. Yes or no? Okay, but then now we have the general formula in front of our eyes. Okay, so what is the formula for this one? So let me use which one we use. Yeah, let us use this one. Okay, we add these numbers 1 unit less and n minus 1. Okay, so what is the answer here? N minus 1 is how much here? 2. And then what in the numerator? This number plus that number 1 unit less, which is 2. Yes or no?
Yes.
The number of ways I can do this, what is the next one? This one plus that one, 1 unit less, which is 3. And then what is here? Come on, say something. What's here? 2. Okay, what is the next one? The next one is the same equation equals to 2. So what happens here? 4, 2. And then if I continue that, what happens here?
7, 2.
7, 2. No.
No.
What is that one? This one plus this one minus 1. 9, 2.
Okay.
Yes? Is that right or not? Okay, so the question mark is the sum of these numbers, yes or no?
Yes. Yes.
Okay,
So it's just what we did previously.
yeah, exactly. So this is something I actually cooked up before that. So this is Pascal identity. But let me test your memory, which you're not that good in. So what is the problem in Pascal identity here? Do you remember?
Yeah.
And what was that?
So we do 3.
Instead of 2, 2, we write 3, 2. Yes? And then it becomes Pascal identity. So I combine them, it becomes?
Should it be 3, 3?
3, 3. That's good. So you're feeling responsibility now. Okay. So what we should do now?
4, 3.
4, 3. And then that next one?
5, 3.
5, 3. And what is the last one?
10, 3.
10, 3. So that's your final answer. Yes?
Yes.
But even you don't know that one, if you don't know Pascal identity, I wouldn't say that this is writing this one is hard by understanding this. Now it is not crazy beautiful, is it?
No.
No, yes, you are. It's not crazy beautiful. It's beautiful, but not crazy beautiful. But there is a crazy beautiful way to come up with the final answer directly. That is crazy beautiful. But of course, crazy beautifulness needs creativity. Yes? So you have to be creative, otherwise you have to live with this amount of beauty. That's it. Okay? Either you have to be so creative to generate a new art. By the way, that's art. You know that in Princeton they give a degree of art to mathematician. So you don't get degree of mathematics or something. You're offered degree of art at the end when you do your PhD in mathematics. Yes? So what happens here if I want to come up with that answer? There is a very nice way to do that, but I will tell you, okay? I will tell you. Let me write this equation. Okay. This is inequality, but I write an equation, okay? Forget about that for the time being. And I would write it as equal to 7. Okay? This, and compared it with that one, I have one extra variable, but instead of having inequality, I have 1. Forget about that problem. I ask you the number of non-negative integer solutions for this equation. Oh, I erased the formula. Do you have it in your memory? What's the answer to this? This you can do with the general formula. Do you remember what was the general formula?
R plus n minus
Xn is equal to R. What was that? N plus R minus 1? Or the other way around? And then?
over n.
N minus 1, yes? Okay, do it for this equation. What happens? Do it.
I'm doing it.
4 plus 7, 11 minus 1, 10.
10.
Yes? And then n minus 1?
3.
3. Is that answer?
Yes.
But is it coincidence?
No.
So So this is the crazy beautiful thing. So instead of solving a problem in 3 dimensions, x1, x2, x3 with inequalities, you go to a higher dimension, which includes 4 variables, and then you solve the problem in that world. You get your answer in your world. And this is, by the way, happening. So this is one idea that people got interested in higher dimensions. Because when you go to higher dimensions, you have more freedom. You can work, you can do whatever you want to do, more things there than your limited version of life. And then when you do something there, you can translate it back into your own language and your life. Okay, so what do you think? Can you, this I want to think about, you think about it. Why do you think that the number of solutions to this equation should match with the number of solutions to this inequality? I guarantee you this is not a coincidence. There is a very nice creative story behind that. And I want you to understand that story. Yes?
In the Conti version, we have more degrees of freedom, and therefore we add one here.
No. No, we want, this is, I want to, because this number is not approximately that number. They are exactly the same. So it means that even there is no one. So of course, you know that the answers to this equation, if I want to give an answer to this inequality, how many numbers I offer to you?
What do you mean?
I mean the same thing, I repeat. If I ask you to give me a solution to this inequality, how many numbers I need to wait for you to present to me? Okay, so I don't know. So give me a solution to this inequality.
10-3.
What?
Oh, sorry.
No, give me a solution to
Okay.
this inequality.
700.
700. This is a solution to this inequality. Okay?
Yes.
But so how many numbers you offer to me?
3.
But if I ask you to give me a solution to this equality, how many numbers you offer to me?
4.
4. Okay? But so it means that you have 4 tuples offering here. One of them, second, third, and it will finish. And then here you offer me triples. 1, the next one 2. And then I want to say the number of triples that you present here is exactly the number of 4 tuples that you present here. It's not obvious unless you have a very nice story or argument why this is true.
Okay.
This is crazy beautiful. I don't know. Do you agree with me? So it means that if you are creative, instead of doing it like that, you can add one variable, and then instead of inequality, you look at equality. But if you understand your story very good, you know that, okay, I got the answer, no matter what they are doing. Yes? To be honest, if you didn't know about the Pascal identity, it was not that easy. You got this answer fairly easily, but it is not that easy to see this number should be exactly that number. Okay, what is that? Do you have any idea why this is the case? Yes.
I think it is if you move x4 to the other side,
Mm-hmm.
then I mean, let's say x4 is 1, then the right hand side is equal to 6, and then the left hand side changes with that.
So the idea is not that bad, but you need to make it more defendable, yes. So you need to know the idea of one-to-one correspondence again. So you need to convince yourself for every single solution of this equation, so exactly like this person who is coding and the person who's deciphering. So you need to understand. So for example, you are in Russia, you are sending a solution to this inequality. The person who is spying in the other country should be able to decipher it as the solution to this equation. If you know how to communicate with your colleague in the other land, then it means that you have the story. So in other words, when you told me 700 for this, which is right, you actually transfer it to your colleague in the other country, how that person deciphered this code to get a solution to this. if you can understand this story, this is, by the way, very powerful. This is the first time, by the way, I'm thinking in that way myself, okay? This is a very good metaphor, yes? So that person sends this code to his colleague there, and that person should decipher it in a way, in a unique way, to get a solution for this equation. When the time is finished, do you know?
55.
Okay. Okay, for example, can you offer me another non-trivial answer? For example, here, let me choose this one to be 2, and then let me choose this one to be 2, now let me choose this one to be 1. Do you agree this is a solution to this inequality?
Yes.
What was the English word I say? I don't remember. When you send the code, what is it called? You telecommunicate or what? You transfer it. So anyway, you transfer it to your colleague. How do you think your colleague will decipher that code to get a solution to this equation? I'm not saying there is a unique way to read the story, but you need at least one version of that story to convince yourself this is working. And I don't know what is your story. This is why I'm waiting for your story. And your story should work for every choice of that solutions, not for one of them. So what Aaron said is right. Can you just use your idea to tell me, if I communicate this with my colleague, how that colleague will take it and change it to a solution to this? Just tell me, because what you said is correct. I didn't say you are wrong. I said that you need to make it more elaborate to be able to promote it as a mathematical proof. So can you tell me, if I send 2 to 1 to this person take it as, anyone, yes?
x4. Or 7 minus x4.
No, tell me, no, you need to write a quadruple here. Yes? So I need 4 numbers. Which 4 numbers they will understand?
2, 2, 1,
2, what?
2, 1, 2.
2, 1, 2, like this? Yes?
Yes.
Okay, so let us check. 2, 2, 2, and then when you add them, it becomes, yes, that's correct. So what you did, you add them up, and then you said subtract it from 7. I don't know why don't you say, or you remain silent. Is that understandable?
No.
Why not? Because let us check.
You're
2,
inventing
2,
numbers.
1, 2, 2, 1. 2 to 1 is a solution to this inequality. Do you agree? And now if I ask you what is this one, you need to add 4 numbers. If you add these 4 numbers, what happens? It becomes 7.
Yes.
So that's right. So this is one story that Aaron made up for us. But it is working. For example, you send this code to your friend.
Uh-huh.
How the friend will decipher it?
7, 0, 0.
7, 0, 0, and 0. So what we are doing here, we are counting the number of quadruples.
Yeah.
What we were doing there, we are counting the number of triples. They are in the same, the numbers are the same. Is that right? Yes, it's very obvious. Yes. So you're tired a little bit probably, yes?
Is it because you subtract x1, x2, x3?
Yeah, I followed Aaron's story. That's why I'm surprised why he cannot defend his idea. Your idea was exactly the idea. Yes? So can you, for example, let me test another one. Here, for example, I have 2, 2, and 3. Oh, sorry, 2, 2, and 3 here. Is that acceptable for that inequality? Yes, because when I add them, of course, it becomes exactly 7. How do you decipher it?
2, 2, 3, 0.
2, 2, 3, 0. Okay? Yeah, that's, no, 2, 2, 0.
No, it's right.
Yeah, that's correct. 2, 2, 3, 0. Now let us change the role. Now assume that you are in Russia. You send this code to your friend. The friend should decipher it as a code for this inequality. How the person acts. Just drops the last one and gets the answer. So hopefully you are convinced that the number of triples in this way and the number of quadruples in this way are the same by the story that Aaron cooked for us. Yes?
Can you say that the last number is used so you achieve the number?
Yeah, exactly. So that is exactly, this solution is not mine, by the way. I remember the excitement I got from the solution when I saw.
So
Okay?
If you can think of it like an x4 modified.
The lesson is finished, by the way. Thank you.
So it fits to the original answer.
Yeah.
The original set answer.
Yeah.
Okay.
So there is no teacher can teach you how to think in this way unless you see some sample problems. By each problem that you see, go into your brain, fine-tune these gears there, so that it works better next time. Yes? That's the only purpose of mathematics. And it, by the way, doesn't matter, are you working mathematics? By the way, have you seen my message? So some of you have registered, some of you haven't. But even if you don't want to come to the lessons, it doesn't matter if you register, then I will publish something. I will talk about abstract mathematics. I changed my mind. I call it transition to advanced mathematics because might be advanced mathematics is a little bit terrifying. Yeah. Thank you very much.